everyone, in this video we're going to be talking about the graph of a function. So we spent a lot of time in the last few videos talking about functions. Now we're going to focus on their graphs. So we're going to identify the graph of a function, and then we're going to obtain information about the graph of a function. So a lot of times what we're interested in is high and low points. We call those maximum and minimum values. Okay, so first let's talk about this called vertical line test. And the point of this test is to figure out if you're working with a function or not. So it says that a set of points in the xy plane is the graph of a function if and only if every vertical line intersects the graph at most one point. Alright, let me explain this because it's a little wordy, but pretty much you have graphs and sometimes they represent functions, sometimes they're just graphs of equations, but not functions. Remember in the previous videos we learned all about functions and we learned the definition, what it means to be a function. And so if you're only looking at the graph, you can tell very quickly if you start drawing vertical lines and you only hit the graph once or not at all, then it is a function. Okay, so real quick reminder, in order to have a function, remember this, I talked about a vending machine example, but if you have one input, it can only produce one output at a time. Okay, so that's a function. What's not a function is if you have something like this. One input somehow magically produces two outputs. So that's not a function. And so our vertical line test basically tests for that idea right there. Okay, so let's take a look at this example. Which of the graphs are graphs of functions? So you can start drawing vertical lines. Notice this line here. Based on my image of my graph, it doesn't look like it hits the graph at all. Over here it hits it once, it intersects once, here it intersects once, and so on. So it hits the graph or intersects the graph once or not at all, and that would be the graph of a function. Very similarly over here, oops, that's not a very vertical line, but hopefully you get the idea. Intersects once, it intersects once, and so on. So that would be the graph of a function as well. So any vertical line you could draw, any one you can imagine, would always hit the graph once or not at all. Technically, it still hits it, like, even though I'm saying not at all, if this were to continue to go like up, we would see that it would intersect just once still. Okay. Alright, take a look at this one. Which one of these are functions? Neither one, because this vertical line doesn't intersect the graph at all, so that's okay. This vertical line intersects the graph exactly once, but the next vertical line intersects the graph twice, and this would not be the graph of a function. And so if you think about it, for this one x value right here, so this x value right here, let me change colors so it stands out a little bit. So this x value on my x-axis, this x value has this y value corresponding to it and this y value corresponding to it. Okay, because that's where the points are. So 1x, it's the situation where 1x gave us 2 y's, and that is not a function. Okay. Very similarly with this next example, we can draw vertical lines, and we'll find pretty quickly that we're going to intersect our graph more than once, and so that's also not the graph of a function. These are equations, yes, but they're not functions by definition of a function. Okay, so just a note here of exactly what we were talking about. For this particular x value of -2, we have two different y values, 1 and -1. So that's example why that one's not a function. Okay, so how about this one here? Obtaining information from the graph of a function. So this is our second objective. So this time we're starting with the graph of a function. It's what we have over here in blue. And we want to know some things about the function based on its graph. Okay, so question A, what are the following? So remember, math is this language of symbols. So what this means, you want to translate it so you can answer, is, let me put it over here to the side. Alright, so this is what it means. What is y when x is blank? And the blank is what's in the parentheses. So it looks like f of 0, so that means what is y when x is 0? So this is math language, this is just symbols. And then if you can understand the symbols, you translate them to English over here, and then you can answer the question. So one of the harder parts in math is just understanding what's being asked of you. Once you understand it, you translate it, then you can go ahead and answer the question. Okay, so for that one, x is 0 on the x-axis right here. And so what is the corresponding y value? Well, the point is 0, 0, so y is 0. And then similarly for the next two, f of pi over 4, that would say what is y when x is pi over 4? And so you would look at pi over 4 on the x-axis, and you would say, well, what is the y value? The y value is right here, it's 2. So the answer to that one is 2. Okay, and then we'll go ahead and go through these, but I just wanted to talk about that one real quick. So what is the domain? Remember, that is all of the x values that you can plug in. So the domain is all the inputs. So this is a translation, just rewording it so that you can answer it. Okay, so what's the domain of the function? What are all the x values that the graph includes? What is the range? So range is the outputs, very similar to the domain question, but just change this to y values. So range is the same thing that I just wrote for domain, except it's outputs. So you would say y values. And then list the intercepts. So those are where you cross the x-axis or the y-axis. How many times does the line y equal -1 intersect the graph? We'll talk about that. For what values of x does f of x equal -2? For what values of x is f of x greater than 0, or in other words, positive? Okay, so let's go through these. So part A, we were asked 3 different things. We were asked, what's f of 0? The question was, what is f of 0, meaning what is y when x is 0? So we did that one already. Right here, when x is 0, y is also 0. Okay, so the answer to that question is 0. And then we were also asked, when x is pi over 4, so what is y? The question was f of pi over 4. So what is y when x is pi over 4? So that one we already figured out as well. When x is pi over 4, y is 2. So the answer to that one is 2. And then the next one, the last one from part A, said f of 7 pi over 4 was the question. So when you translate that, it says when x is 7 pi over 4, what is y? So 7 pi over 4 is right here on the x-axis. Notice where it's at. And then so you go down to your graph, the point is here. And if it wasn't labeled, which it is, it's labeled as -2, you would just go over to your y-axis over here, and you would say it's -2. Okay, so that's the answer for that one. So f of something, anytime you're asked f of something, f of some number, it's really asking you what is y. So find y when x is that number. Alright, part B said to find the domain. So this is pretty much all of the x values that the graph includes. And as long as you recognize that the graph is continuous, there's no holes or jumps or anything. If you take a look at your graph, if I were to start drawing this, I would never pick up my pen until I'm done, okay? And so it's a continuous function, it's smooth, there's no jumps or gaps or anything, and so the blue graph covers all the x values from the starting x value to the stopping x value of our function here. And so the first x value, if we start from the left, right here x is 0, and we have graph everywhere in between until we stop right here, and we stop when x is 2 pi. Okay, so all in between those two x numbers, there's blue graph, there's points. There's infinitely many points on this graph, all the way in between, corresponding to all of these x values. Okay, so we have from 0 to 2 pi is giving us any point on the graph, and those are our x values, so this is the domain. And so the domain, you can answer it in set builder notation, which is this one here, or in interval notation, which you'll probably do this one more often, this interval notation. So let me star that one. And remember how interval notation works. You have a starting and a stopping point. So let me just kind of talk about this for a moment so it's clear. You tell in the interval where you start, and then you also tell in the interval where you stop, with a comma in between. Now the ends of the interval matter. You're going to use brackets if you can equal the endpoints, like if there's points there. So I'm going to say if you can equal, if there's a point, or point exists. Okay, Because if you're looking at the graph, you're really interested in the points. So if the point exists, why I said equal is because if you're using these inequality symbols, you have this little equal bar here. Okay, so that's why I wrote the word equal. If you cannot equal the endpoints, if the point doesn't exist, you use parentheses. So that would be if it's not equal, if you don't see little equal bars on your inequality like we do here, or if the point doesn't exist. Like it gets really close, but you have like an open circle there. Point, say DNE, does not exist. Okay, so that's our domain. Now the range, part C was what is the range? The range is all the y values that the graph covers. Very similarly, this graph, like I said for domain, doesn't have any gaps or holes or anything. And so you look at the graph and there's blue graph everywhere from this is the lowest y value all the way to this is the highest value, y value. There's points everywhere in between. Okay, there's all these points in between all these y values. So your y numbers that the graph includes are all these numbers in between -2 and 2. And so the range is in set notation like this, all y's such that y is greater than or equal to -2 or less than or equal to 2. And then this is our interval notation. Notice we start at -2. You always start with the smaller number, whether you're talking about domain or range. So you start at -2 and you have y values all the way in between until you stop. There's no more y values above +2. There are points that you can equal. So notice there are actual points at 2, up here at 2, and then down here at -2. So that's why we have brackets here. Okay? Okay, so watch the graph. So those are the intercepts. So we have a bunch of x-intercepts and actually only one y-intercept, because these are all on the x-axis only. X-intercept, 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 x-intercept. But this one is x and y because it touches both axes. So this is a x and y intercept right here. This one's both. The rest are just x-intercepts. And then part E, so you have to get to y is -1. I know this is a little misleading on the picture, but it should be right here at the line. So y is -1 here, but you draw up yourself a line so that you can see how many times you hit the graph. Okay, so you pick the y number. We're told y is -1, so we go down to -1 and we draw a line across. And then we say, okay, we hit the graph once, twice, 3, and 4 times. Okay, so now part F asked about what is x when f of x is -2. So f of x is y. Remember, f of x represents your output or your y value every time. So you say f of x is the same thing as y, and that's -2. So I go down to -2, and then I want to know about those points and the corresponding x values. So let me clear up some stuff from part E. Okay, so I say y is -2, f of x is -2, and then I find the point on my graph right here, and I go up and find the x value, excuse me. And so this x number right here, it's actually labeled down below, but it's 3π/4. And then my next one, I would keep going. I would say, okay, oh, I hit the graph again right here. I have another y value of -2, and I would go up and I would say, okay, x right here, x is 7π/4. Okay, so I know when y, f of x or y is -2, when x equals 3π/4 and 7π/4. Those are my x numbers corresponding to this y number. And then part G, when is f of x greater than 0? That's the same thing as saying when is y positive? When is y positive? If it had an equal bar underneath this inequality symbol, then we would say positive or 0, but this is strictly positive. Okay, so what we want to do is we want to answer in terms of the x values. Okay, so when is y positive? So y is positive anywhere above this line, anywhere above the x-axis. So y is positive up here, but you want to answer in terms of the x values. So when is y positive You always want to answer in terms of the x values. So you have to take a look at the graph and determine when this happens. Okay, so it's positive up here. Now let me explain this answer, because this is the answer. Great, so let me clear off my scribbly line. The yellow area is when y is positive. Okay, and take a look at the answer. So all of these x values starting at 0, so this is x is 0, all the way to here, pi over 2. So anything in between, so this could be 0, this could be 0.1, 0.2, 0.3, 0.4, 0.5, and so on, all the way to pi over 2, which is 1 point something. All of those x values have a corresponding point on the graph, a y value, that's positive. Okay, so that's this part. It's saying x is 0, my starting x, until my stopping x. So let's write that out. This is my starting x, and then this is going to be my stopping x, where I stop. Stopping x, because after pi over 2, that's when the graph goes negative, and I don't care about that right now, so I don't want this right now. Again, it picks up right here at pi, which is 3 point something, 3.1, and so we have all the way until 3 pi over 2, and so this would be like 3.2, 3.3, 3.4, and so on. All these x numbers in between, I have y values on my graph that are positive, okay, because this is positive going up over here, positive. And so that's this part. I have another starting x and another part of x where I stop. Okay. So the question is asking you, when y is positive, what are all the x numbers that give us those points? It's too many to list. It's like infinitely many. There's so many points in here. I could keep scribbling little dots. There's so many points to list. It's going to be impossible. So what we do instead is we use these intervals. We say any x that I pick, any x that I choose between 0 and pi over 2, I'm going to get a positive y. Any x that I pick between pi and 3 pi over 2, I'm going to get a positive y. Both of these, no matter what I pick, y is positive. Okay, so this symbol right here, this is or. This is the union symbol. You can say the word or in place of it. Okay, so that is the answer. So that might be new to you if you've never seen interval notation like this, but it's asking you about x. It's exactly the same as this statement above, just written in interval notation. Okay, so you can also do it like this with the inequalities. Okay, so now let's consider this next example. New function, the function is x plus 3 over x plus 4. And last time we were given the graph, this time we're given the function, but we're going to find all of these things. The domain, we're going to answer this question about the point, is the point 1 comma 3/4 on the graph. Part C, if x is 2, what's y? That's how you would translate this. What is f of x, what's y? And then what would that point be on the graph? So a point would be an x comma y ordered pair. So we already know, let's just say equals, not or. We already know x is 2, so the question is what's y? So we'd have to answer that. And then part D, if y is 4, what's x? So that one looks like what's x when y is 4 as a point on the graph. And then part E, what are the x-intercepts on the graph, if there are any? And then what are those points? Okay, so the domain, with the domain, you think about every x that you can possibly plug into the function, but because there's so many, you can list them forever and ever and ever, and you'd still not get them all because it's infinitely many. You actually ask yourself, is there any problems? And anytime you have a fraction, you never want to divide by 0, because remember, that is undefined. So this is undefined. If we ever divide by 0, oops, undefined. And so I want to look at a fraction every time my function has a fraction bar. I want to say, oh, I don't want the bottom to be 0. So in this case, if I just say that x plus 4 shouldn't be 0, then if I solve, x should not be negative 4. And so my domain is all x's such that x can't be negative 4. So it's everything but negative 4. And then part B, when x is 1, then what's f of 1? So just plug it into the function. So f of 1 means what's y when I plug in x equals 1. So then just plug it in exactly where there's x's in the function and simplify. So that would just be 4/5. And the question was, is 1, 3/4 on the graph? And it's not, because when you plug in 1 for x, you get 4/5. So 3/4, that's not the y value of plugging in 1. So f of 1 equaled 3/4. It did not, sorry, it equaled 4/5. It did not equal 3/4. So no, that point's not on the graph. Part C, when x is 2, then what's f of 2? So plug in 2 for x, and then simplify. So we get 5/6. So when x is 2, so this is x, what is y? It's 5/6. And that would be the point on the graph when x is 2. And then part D, if y is 4, so remember f of x is y, when y is 4, okay, then go to our function. This time the function, remember, it's always f of x, but that's the same thing as y. So that's saying when y is 4, what's x? So this one's a little bit more work because you have to solve, not just simplify like we did on the last one. So you're going to plug in y is 4 where f of x used to be, and then we're going to solve this. Okay, we're going to solve for x. Okay, so the first thing that I would recommend when you're working with a fraction like this, let me write it off to the side, is I would try to get it to where I no longer am working with a fraction. So what I would do is I would multiply both sides by the denominator, and that's exactly what happened here. So if I multiply the left side of this equation by the denominator, and the right side of the equation by the denominator, and as long as you do something to the left and the right side of an equal sign, it's going to stay equal. So as long as we do it to both sides, it's equal still. This one divides out, and that's how we got this step here. Okay, keep going, and then just distribute. So this is 4x plus 16, and then you want to get your x's on the same side of the equal sign so you can solve. So it doesn't matter if you pick the left or the right. I'm going to go ahead and go left. So I'm going to subtract 4x from both sides. And because I'm moving my x's left, I might as well move my numbers to the right. So I'm going to subtract 3 from both sides. That's where we get negative 3x equals 13. Divide so that x is by itself. So now x is isolated and y is, and the answer is the right side. So negative 13/3. Okay, so when y is 4, x is negative 13/3. And so the point on the graph is x, comma, y. Part E asked about the intercepts on the graph, and think about that. We've learned about intercepts before, but think about why this is the setup for our question. The x-intercepts, we learned this in a previous video, but anytime you want to know when you hit the x axis, you're going to always let y equal 0. Okay, always, because if you think about the graph, let me just draw it real quick. If you think about graphing, then you're going to hit the x-axis anytime you don't move up or down from the x-axis, which is always when y is 0. Okay, so always, 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 if you're looking for x-intercepts, you just let y equal 0. Okay, so in our equation, our function is equal to y, which is equal to 0. So f of x is y, and we want it to be 0. Okay, so we solved this. So same thing like the last one, we multiply both sides by the denominator, and I'll write that out here, but hopefully you see it just divides out. So if I just say x plus 4 on both sides, times here and times here, 0 times anything on the right is still 0, and then it divides out on the left. Okay, and then we just get x is negative 3. So that's going to be our x value for our x-intercept. And we already know our y value is 0. Okay, so that's the only x-intercept. X is negative 3 when y is 0. So that's our ordered pair on the graph. Okay, last example. And this one's more of an application problem. So average cost function. So the average cost, we're going to call that capital C, per drone of manufacturing X amount of drones per day, is given by this function. Okay, so we didn't have to come up with this function. It was given to us from the context of this problem through some kind of research that was done about cost of drones. You can name your function anything you want. We normally name it F, but when we're talking about application problems like this, like cost, it makes sense to name it C. So we named it C, so C of X, where X is the input, and X is the number of drones. So it says X drones per day, so X is the number of drones. And then notice the places where you're going to plug in X if you need to plug it in. It's going to go in 3 spots. Okay, so to determine the average cost of manufacturing 10, 20, 30 drones a day, graph the function for all the X values between 0 and 60. So that's saying from making no drones to making 60 drones in a day. And then create a table, and this would be using a graphing calculator with the table starting at 1 and what X value minimizes the average cost. So we'll talk about that when we get to that one. Okay, so the average cost per manufacturing 10 drones a day, you just plug in 10 for X. So everywhere there's an X, put a 10, and I would definitely use a calculator on this one just to save you some time. Plug that into your calculator. Just make sure that you get your exponent up there, because you're squaring 10 first and then going to multiply by 0.7. And then if you need to on your calculator, you might want to tell it to divide this like with parentheses. So it's $1,940.20 to manufacture 10 drones. So the average cost of manufacturing 20 drones per day, plugging in 20 for X, is $1,200.20. And then for 30 drones, plugging in X is 30, $933.53. So it's looking like the heading toward higher drone manufacturing. It's making the cost go down. But if you think about it, that might not stay that way. Like maybe if you make too many, you're gonna like have to replace equipment, or you're going to use more energy and your bills go up. So you're looking for, and I think it was part E, minimizing the cost. Okay, so we'll talk about that in a second. Okay, so here is the graph. You can use an online calculator to graph this. It's not very meaningful here, so let me actually go ahead and go to Desmos website, and I'll show you the graph there. Okay, so I went ahead and went to desmos.com to graph this to make it a little bit more meaningful. I could see my labels on the axes now, and so I had to do some zooming to be able to get to the graph here. And so anything on the left of 0 doesn't really make sense for the context of this function, because it's manufacturing drones and you're not going to manufacture a negative amount. So anything over here to the left doesn't really matter. So what I want to do is I want to look at what happens to the right of the y-axis here. And so notice this graph, it has this bottom number, we call this the minimum. And so remember the y values, the outputs is the cost. So anything up higher here, cost is higher, so cost is up. Let's see if we can find one of the numbers we plugged in. So when we had plugged in 20, so 20 drones cost about $1,200 if you remember, and so that corresponds to that point on our graph pretty much right here. And so the y values, we want them to be lower to answer the question about minimizing the function cost. And so that we want this low point. So if you take a look at this lowest point, that's 37 for X and 833 for Y. So this is saying when we manufacture 37 drones, it costs us the minimum amount that it would for any other amount of manufacturing drones. So $833.69. And it, again, like if you think about it, it could be for a number of factors. If you manufacture too few, you're paying for equipment that's not being used, or you're overpaying employees and they're not having to do the work. Anything past 37, again, your costs are going to go up. Maybe you're using more electricity because you're producing too many, and lots of factors would play into why 37 would be the ideal number. But for us, we just know that based on the graph, graphically, that is the best option. Okay, and so for the last part, if you use a table, we just, well, on the graph, we just went ahead and clicked on the lowest point. But if we had a table of values, we would see that 37 drones would minimize our cost to about $883.77 per drone. Okay, so that is all about our graphs and of our functions. Thanks for watching.